In 1981, the Vatican invited a group of cosmologists to a conference, and at the end we were granted an audience with the Pope. He told us it was perfectly acceptable to study the evolution of the universe after the Big Bang, but that we should not inquire into the Big Bang itself, because that was the moment of creation and creation belonged to God. I sat there relieved that he did not know the subject of the paper I had just presented at that very conference, a paper proposing that the universe has no beginning at all. Let me show you what I mean, and let me start with a question that sounds simple. Is the universe finite, or is it infinite? Most people pick one without thinking very hard, but both answers collapse under scrutiny. An infinite universe filled with stars burning for an infinite stretch of time would flood every possible line of sight with starlight, and the night sky would not be dark but blindingly bright in every direction. This puzzle carried the name Olber's paradox, and it troubled astronomers for centuries. A finite universe creates the opposite problem, because a finite universe has an edge, and if it has an edge, what lies beyond it? More space would mean the universe is not truly finite, and nothing is a concept the human mind cannot even picture as something you could stand next to. Both answers trap you. Immanuel Kant argued that each leads to a logical absurdity, and he called these contradictions antinomies. Isaac Newton assumed infinite space, but could never resolve the paradoxes that followed, and for centuries after him nobody found a way out. The escape route came not from philosophy but from geometry, and to understand it you have to abandon everything you think you know about what the word boundary means. Consider the surface of the earth. You could in principle measure every square meter of it, and it has a definite, calculable area, which makes it finite. And yet there is no edge anywhere. There is no place on the surface of the earth where you come to a wall and find a sign that reads, "End of surface." You can travel in any direction indefinitely and you will never fall off, because you will simply come back to where you started. The surface of the earth is finite but without boundary, a two-dimensional surface that curves around to close on itself in 3 dimensions. But here's the thing, the principle extends much further than that. Could the 3-dimensional universe itself curve around and close on itself in a higher dimension? Albert Einstein showed that it could. His general theory of relativity, published in 1915, revealed that matter and energy warp the geometry of space-time, and that space is not a fixed stage on which events play out, but a dynamic fabric shaped by its contents. Depending on how much matter and energy the universe contains, that fabric can curve back on itself, producing a universe that is finite in volume, yet has no edge whatsoever. An astronaut traveling in a straight line through such a universe would eventually return to her starting point, just as a ship sailing a straight course on the ocean eventually circumnavigates the globe. That only resolves half the puzzle, because even if space is finite without boundary, the question of time remains. The universe is expanding, and Edwin Hubble demonstrated this in 1929 by measuring the redshift of distant galaxies, which is the stretching of their light toward longer wavelengths as they rush away from us. The farther a galaxy sits from us, the faster it recedes, every galaxy fleeing every other galaxy, while the whole fabric of space stretches like the surface of an inflating balloon. Run that expansion backward, and every galaxy rushes toward every other, the temperature climbing from 1,000 degrees to 1,000,000 to 1,000,000,000, the density rising beyond anything found in the core of the heaviest star. In the late 1960s, Roger Penrose and I proved something about this backward journey that changed the direction of my career. Our singularity theorems demonstrated that if general relativity is correct, the universe must have begun in a singularity, a point where the density of matter becomes infinite and the equations of physics break down entirely, a point where time itself comes to an abrupt stop. That proof established my early reputation, and then I spent the next 30 years showing why it was incomplete. The problem with a singularity at the beginning of time is straightforward. At a singularity, the laws of physics cease to apply. They give no prediction and offer no explanation, which means a singularity is not an answer, but the place where answers stop. Most people hear about the Big Bang and simply accept this, imagining a moment of creation, a cosmic explosion at the start of time, and then they ask what seems like the most natural question in the world: what happened before the Big Bang? I want to show you why that question is not difficult but meaningless. Think about the North Pole. The surface of the Earth narrows as you travel north, and lines of longitude converge, drawing closer and closer together until at the pole they all meet in a single point. Now consider what it would mean to ask what is north of the North Pole. The question has a grammatical structure and it sounds perfectly legitimate, but it refers to nothing. There is no answer, not because we lack the knowledge, but because the question itself has no content, since the concept of north simply ceases to apply at the North Pole. That is not merely a convenient analogy. It is, in a very precise mathematical sense, the key to understanding the origin of the universe. In 1983, James Hartle and I proposed what we called the no-boundary condition. The idea runs as follows. In everyday experience, time behaves like a line, stretching from the past into the future with one moment following the next. But when you apply quantum mechanics to the very early universe, when the universe was far smaller than an atom, time stops behaving like a line, and the distinction between time and space blurs completely. To make this precise, I used a technique involving what physicists call imaginary time. The word imaginary here does not mean fictional. It is a technical term from mathematics. Ordinary time is measured in real numbers, 1 second, 2 seconds, 3 seconds, while imaginary time is measured using imaginary numbers, which involve the square root of -1. If that sounds exotic, consider that the engineers who design your electrical circuits use imaginary numbers every working day because they are the backbone of alternating current analysis. The same mathematical structure that describes the electricity flowing through the walls of your house also describes the origin of the universe. When you replace ordinary time with imaginary time in the equations of general relativity, time becomes indistinguishable from a direction in space, which means it becomes another spatial dimension entirely. I called this framework Euclidean quantum gravity because in imaginary time the geometry of the universe becomes Euclidean, smooth, and well-behaved with no singularity and no jagged edge where physics falls apart. What that means is staggering. If time becomes like space near the origin of the universe, then asking what happened before the Big Bang becomes exactly as meaningless as asking what is north of the North Pole. The universe does not have a boundary in time any more than the Earth's surface has a boundary in space. Time does not begin at the Big Bang the way a road begins at a wall, because instead time smoothly rounds off like the surface of a sphere approaching its pole. The Big Bang is not an edge. It is more like the South Pole on a globe, a point where things converge, but beyond which the question of before has no meaning. Let me make that concrete by asking you to imagine the entire history of the universe as the surface of a globe. The South Pole represents the earliest moment, the Big Bang, and as you move northward, you move forward in time. The universe expands, galaxies form, stars ignite, planets coalesce, and life emerges. Chemistry becomes biology, and biology becomes consciousness. You are somewhere in the northern hemisphere right now, and the South Pole lies in the deep past. But the South Pole is not an edge or a wall, and it is not a beginning in the way you normally conceive of one. It is simply the southernmost point, and if you stand there, every direction you look is north. You cannot go further south, but you have not hit a boundary, because the surface is smooth and continuous under your feet. The Big Bang in the no-boundary proposal works exactly the same way. It is the southernmost point of time, and there is nothing before it, not because something prevents you from going there, but because before is not a direction that exists. What that tells you is that the question of what caused the Big Bang assumes time extends backward beyond it, and the no-boundary proposal says it does not. Asking what caused the universe is like asking what is south of the South Pole. The universe did not need a cause because there was no time in which a cause could have operated, which means the universe can be its own explanation. That troubled people. It troubled many of my colleagues, and it troubled the question I had sidestepped at the Vatican. If the universe has no boundary and no beginning in the ordinary sense, then what place remains for a creator? But before we reach that question, there is something deeper to understand, because the no-boundary proposal does not give you a single definite history of the universe. It gives you every possible history all at once. Richard Feynman introduced this technique into quantum mechanics and called it the sum over histories, where a particle does not take one path from A to B, but takes every conceivable path, and you calculate the probability of any outcome by summing contributions from all of them. Applied to the universe as a whole, this means the cosmos does not have one past. It has every possible past, each weighted by a probability. The history we observe, the one with galaxies and stars and carbon-based life, is the one with the highest probability, given the no-boundary condition. And that brings us back to the original question. Is the universe finite or infinite? In the most probable histories consistent with the no-boundary proposal, the universe is spatially finite, curving back on itself with a definite volume, just as the surface of a sphere has a definite area. But it has no edge, no wall, and no outside. Within this finite structure, the universe may be effectively inexhaustible, containing more particles than you could count in a lifetime, with regions of space expanding so rapidly that their light will never reach us, and black holes whose interiors remain permanently hidden from view. And here is where this framework does something that still astonishes me. because it explains features of the universe that would otherwise appear miraculous. Consider the flatness problem. Measurements of the cosmic microwave background, which is the afterglow of the Big Bang, first detected by Arno Penzias and Robert Wilson in 1965, reveal that the geometry of the universe is extraordinarily close to flat, Euclidean like a tabletop, rather than curved like a sphere or a saddle. Data from the Planck satellite launched by the European Space Agency confirmed this to stunning precision, showing the universe is flat to within roughly 0.5%. Any slight deviation from flatness in the early universe would have been amplified enormously over 14 billion years, which means the universe should be wildly curved by now, and yet it is not. The no-boundary proposal explains this because when you sum over all possible histories with no boundary condition, the histories that dominate are the ones that are very nearly flat. The universe is flat not because someone tuned it that way, but because flatness is the most natural outcome of a universe with no boundary. The same reasoning applies to the large-scale uniformity of the cosmos. Temperature variations in the cosmic microwave background amount to only 1 part in 100,000 across the entire sky, and that uniformity is one of the great puzzles of cosmology. Inflation, the theory proposed by Alan Guth in 1981, provides a partial answer by describing a period of exponential expansion in the first fraction of a second that stretched tiny regions into cosmic scales. But the no-boundary proposal goes deeper. It suggests that uniformity is a natural consequence of the universe's quantum origin, because in imaginary time, the early universe is inherently smooth and symmetric, like the surface of a perfect sphere, and the uniformity we observe reflects that underlying mathematical structure. And here is the part that most explanations never reach. The no-boundary condition does not merely explain what the universe looks like. It explains why the laws of physics are the way they are. Why 3 dimensions of space? Why matter instead of antimatter? Why these particular constants? In the no-boundary framework, none of these are arbitrary choices imposed from outside. They are the properties that correspond to the most probable histories in the sum, which means the laws of physics are not written into the universe by an external hand, but emerge from within the mathematics itself. I continued refining this idea for the rest of my career, and in one of my final papers, published in 2018 with Thomas Hertog, I revisited the no-boundary proposal and argued that it predicts a far simpler and smoother universe than we had originally calculated, one with a finite number of distinct structures, rather than the wild proliferation of forms some physicists had feared. The universe described by the refined no-boundary condition is not a chaotic multiverse of infinite variety, but something more elegant, constrained, incomprehensible, and finite. Not everyone agrees, of course, and Neil Turok, among others, has proposed competing models. That is how science is supposed to work. The argument is not settled, but the no-boundary proposal remains what I believe to be the most economical account of why there is something rather than nothing. Which brings us back to the question I was not supposed to ask at the Vatican. If the universe is entirely self-contained, having no boundary or edge, no moment of creation, and no beginning or end in imaginary time, then it simply is. What place then for a creator? I am not offering a proof of absence. I am observing that the universe does not appear to require anything outside itself to exist, and you may draw your own conclusions. The Pope, as far as I know, never read my paper, but I suspect he would not have approved. Every time you look up at the night sky, you are looking at something finite that contains no edge. The darkness between the stars is not evidence of emptiness, but evidence of a universe with a finite past, a universe in which light has only had 14 billion years to travel because time itself is finite. Olber's paradox is resolved not because the universe is infinite, but because it is not infinitely old, and yet there is no wall where it stops, because it curves gently and imperceptibly and closes on itself. That is what the universe really is. Not a room with walls and not an endless void. It is something your language does not have a word for, a finite thing without an edge, a thing with no beginning that has not existed forever. I have spent my career in a chair, in a single room, in a single building, in a single city, and I could not move my body across even the smallest room, but the reach of the human mind has no such constraint. We are on a minor planet of a very average star in the outer suburbs of one of 100 billion galaxies, and yet we can understand the universe. That makes us something very special.